Okay, so let's start now. We're going to look at instantaneous velocity and speed. So like I said, previously we were talking about just kind of going a little bit at a time or average. Now we're looking at instantaneous, and this is where calculus becomes important. This is basically why calculus was invented. Oh, it even says that. Calculus, yay. Okay, so instantaneous velocity, do this is the definition of the derivative, as you see in calculus. Yay, calculus, it's a derivative. Slope of the tangent line. So basically the idea is like we were doing before, we were taking the little like from here to here. Oh, we're going to go from here to here closer, from here to here closer. Oh, look, if we go super duper close, we basically got ourselves a tangent line. So the instantaneous velocity is the derivative of the position. Okay, so I'm going to say that again. The instantaneous velocity is the derivative of the position graph. Okay, this is like one of the most fundamental things they probably told you in calculus, but if you were like me, you were like, that's an actual application problem. I don't care. I'm just trying to get an A in calculus or a C in calculus or in anything in calculus and just move on. Regardless, instantaneous velocity is a derivative. Okay. Yay. Okay. So you may or may not have had a professor in calculus that made you do graphs from other graphs. Like if this is the something or other graph, do the derivative graph. And you were like, this is awful. I don't want to do this. So here's a reminder on how to do that. Oh, come on, silly little pen. You're gonna have to be a good pen for me. Okay. So if this is position over here on the left, then on the right, we can do velocity by saying, well, basically, what's the derivative? Velocity? It's just, okay, well, we're going to pretend that I'm writing velocity. Oh, lordy be. Come on, OneNote. Velocity. There we go. Apparently likes cursive today. Okay, there are important points where things happen. I'm going to call this at, we'll pretend this is at 0.5 and this is at 0.9. This is at 1 second, right? Okay, so things change. So we know derivative means slope, hopefully, and we can tell that the slopes change at, like this is a slope, slope, and slope, and slope, right? Okay, so that means that over here, we're going to have something at 0.5 and at 1.0 and then at 2. That's in no way to scale. So hold on, we'll try that again. So 0.5, we'll try this better. How about we start with 2 and then do 1 and then do 0.5. There we go. Okay. So if we look at this, the position is going, now I'm saying the position is going up. The position is going forward. It's going from 0 to 0.5. Okay. And it is a constant slope. So the derivative of that is just the slope. And because I'm super good at math, I can figure out what slope is because I calculated slope a whole lot of times. Slope is just rise over run, so it's 0.5 over a distance of 0.5, so that interval is just slope equals 1. So slope for that first section is 1. So, you know what's funny is I already know I'm going to have to do something. So I'm going to do this like this. And then do this like this. Ooh, forgot my T for time. Okay. Okay. You'll see why I did that in a minute. So here, between 0 and 0.5, it has a slope of 1. Okay. Now, from 0.5 to 1, it has a slope of 0. Okay. Because the derivative of that line would be 0 because it would be like, you know, mx plus b, but here m would be 0, so that's the slope. Okay. So that means that the slope of that part is right here. And now we need the slope of this dude over here. So m2 equals 0. And m3, let's see. So this is a drop. m3 drops 0.5 and it goes a distance of 1. So this was a height of 1. And now we have a slope of negative a half that goes from 1. Come on, girl. 1 to 2. All right, and we can just connect these, even though the mathematician in my brain freaks out. The engineer in my brain tells me it's fine, and the physicist in my brain is upset at both of the other parts of my brain. So, okay, so this would be the graph of velocity. So at some point, somebody said, if you're given this graph, can you draw the derivative of this graph with this graph? And you're like, this is stupid. Why would I ever want to do that? And the answer is because one day you're going to have to do it in physics to understand where position or how position and velocity are related. So again, the idea is position, velocity. So now what I can say is now I can look at this graph and they're like, well, how fast are you going at 0.25 seconds? And it's like, oh, I'm going 1 meter per second. So I'm going 1 meter per second if I'm in this time period. Well, how fast are you going at 1.5 seconds? I'm like, well, actually, I'm slowing down at negative a half meter per second. Or not slowing down, I'm going, hold on, let me say this better. I'm not slowing down, I'm going backwards. Ooh, I can't believe I almost said that. Okay, so come here. Ooh, I can't apparently. Sherps, there we go. Yeah, okay, I just said something super dumb. I'm not slowing down, I'm going backwards. Slowing down has to do with acceleration, which would be the derivative of this, which, I mean, I guess I could do that one too. Let's just talk about it because we're here. If I was going to talk about acceleration, acceleration is just the derivative of velocity because it's how fast is your velocity changing. And this is actually kind of a boring graph. Acceleration with a bad, okay. That was supposed to say acceleration, but it's with a bad marker. Acceleration with respect to time. Okay, so I've again got my kind of breakpoints here, here, and here. This one. Okay, but now look, what's the slope of this dude here? 0. What's the slope of the next dude? 0. What's the slope of the next dude? 0. So essentially, there's no acceleration because we're always going a constant velocity. We're just going a constant velocity in different directions, I guess. So essentially what this dude is doing is he's going doop de doop de doop de doo, and then he's staying there, and then he's going do to do to do to do to do, and he ends up where he started. So it takes him a half a second to go there and a full second to get back, and he like hangs out for a half a second. Okay, so that's basically what this graph here has told us. So there's 3 different ways of explaining this. Is he goes forward a half a second, and then he doesn't do anything. He has no velocity, and then he has a negative velocity here. And then here this shows us that whenever he is moving at a constant speed. He's neither slowing down nor speeding up. He is just moving at a standard little turtle pace. Okay, so hopefully, even though I kind of messed up the wording, it's very, very easy to mess up the wording because we get really used to saying things a certain way. Um, just kind of along there. Oh, there, look at that nice little graph. So look, I already done that. Already done that. All right, so this is what we talked about already with speed. Um, Instantaneous speed, doop de doop de doo. Oh, well, look at this. If I deeply cared about practical applications, I would care about those things. Okay, so calculating instantaneous velocity, it's just straight up derivative of a position function. So, for example, let's look at this problem down here. It's going to give us the answer, but I'm not going to look at it. Y'all can look at it. Here, I can. That's not really going to help, but okay. So we have the position particle here, and all right, so if a position is given by this, then using blah, 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 find the instantaneous velocity. So velocity is dx dt. Pen. We had a long conversation about how you were not going to be a dumb pen anymore. Okay. Now, I always recommend writing that definition just because it's an important one. So ddt of, I don't like it how they put it in a weird order. I like my stuff to go in reverse order. So plus 3t pachonk. And so because I am just kind of super awesome at taking derivatives, oops, that's my equation for velocity. So velocity with respect to time is given by this equation. So if I wanted to find the instantaneous velocity at 2 seconds, like it's asking for, I just plug in v at 2. So I could be like, so v at 2 is 1.5 times 4 plus 3, which is like, what, 6? I feel like it should be 6 plus 3 is 9. Did I get that right? Oh, I did. 9 meters per second. You should label stuff. I need to be better about that. All right, and then calculate the average velocity between those two. Now, whenever it's asking for the average velocity, it's not asking you to plug in velocity values and then average them. It's basically saying, given those two positions, what's the averagey time it took to get there? So that's very annoying, but maybe it makes sense. Because remember, this is the definition of instantaneous. And that's like we just did this, and now it's asking us for this. So we just gave it the slope of that blue line here, and now it's asking us for the slope of the pink line. So what we need to do is find this position and find that slope. Okay, so you're not gonna like do anything weird. You're just gonna find each position and then calculate a slope between those 2 points. So the first position was, okay, the first position was x at 1 is 3 plus 0.5, and x at 3 is, oh, I'm definitely not going to do that in my head. 3 times 3 plus 0.5 times 3 cubed. Yeah, 22.5. So the average velocity is going to be that 20, come on, 22, maybe, if I can get it to right. Hold on, let's delete that and see what happens. The average velocity is 22.5 minus 3.5 over the change in time, so that's 3 minus 1. How did I know it was 3 minus 1? Well, you know, this is the xy pair. The xy pair is x was, well, the yt pair. I don't know. It's the unit pair. If I graphed it, the 3 goes with the 22 and the 1 goes with the 3.5. So if I switch these, then I have to switch the 3 and the 1. So as long as you're consistent with what you put on the top order is on the bottom order, then you're fine. Okay, so 22.5 minus 3.5 divided by 2 is 9.5. So an average velocity of 9.5 seconds. So average velocity is 9, come here, 9, right, there we go, 9.5 meters per second. Okay. All right, so average of 9.5 meters per second. So that's pretty great. Does that make kind of sense? Okay, okay. So this is um, the speed of the particle of these times. That's interesting. Okay, so this is again going to be the same thing. You know, we're going to take the derivative, and then since it's asking for the speed is just considered like whenever I'm driving in my car and I'm going this way, my odometer says 30 miles an hour. And if I'm going this way, my odometer still says 30 miles an hour. My speed is 30 miles an hour. It's not like it says speed limit is negative 30 miles an hour if I'm going the other way down the highway. So just kind of a physics dorky vocabulary thing. Speed is always going to be just kind of a positive number. Velocity is the one that's going to have the plus or the minus because again, it's the vector. Velocity is a vector. Speed is just a scalar. Okay, so that's kind of an important point. And if you get confused, just remember that a speed limit is never negative. Okay, speed limits are never negative, therefore speeds are always positive, and then we take it from there. So again, here you can kind of see if you understand how derivatives work. Um, that the derivative, or the, I don't know, like if this is an x squared, the derivative of an x squared would be, well, this would really be a negative 2x squared because it's a downward face. This isn't really what the equation is, but it's a parabola facing down. So x squared, I'm going to put ish for my equations. This is an x squared ish. The derivative would be negative 2x, so it's a downward facing slope. And then the derivative of that would just be like 1 ish. So you see, or 2, I guess. So um, you see that this becomes, oh, this is actually not even acceleration. Sorry. I thought we were going to acceleration. It's like, that doesn't look right. So, but what we've done here is on that negative 2x, chirps, this negative part here gets reflected back up to make it be a speed. Honestly, I think I freaked out, or didn't freak out. I didn't even look at this because I've never seen this kind of graph before. This you're not going to see a whole lot because it just doesn't come up. Really, the reason we're having this big discussion is so that you stop using the word speed. Is we pretty much do this and then we never use the word speed again unless this is just a really, really weird physics book. But once you get into anything past this class, everything's going to be defined in terms of, velocity and stuff like that. So hopefully this is something to get you started. All right.